So today I'm going to present a joint paper with Debapriya and Yair. Both of them are on this workshop, so if you have any questions, feel free to ask them. They will answer. Also, patent licensing from 3 to 2-part tariff. Let me first introduce the background story. Okay, so we are also studying an outside innovator with a cost-reducing innovation. So with this innovation, the production cost can reduce from the original level C to some C minus epsilon. So epsilon is the reduction level. And we're considering a quite general patent licensing scheme, which includes 3 very popular and widely used payment methods. The first one is fixed fee. Here, fixed fee. It's like you pay me upfront some amount, and however you use that technology, I don't care. And the second one is per unit royalty. This is a quantity-based royalty rate. So for each unit you produce, you pay me $1. And the third one is ad valorem royalty. This one is a percentage of the revenue of the sales. It's like if you make $100 sales, you pay me 5%. And in this paper, we consider any combination of the 3 methods. Of course, the 3 instruments that don't have to be positive at the same time. So if the innovator chooses to set the per unit royalty R equals 0, then this 3-way reduces to a 2-way, a 2-part tariff, or it can be reduced to a pure upfront fee sometimes. So this is the payment schemes and licensing policies.
Do you allow the sum of the fee to be negative?
No, we don't. They have to be non-negative.
I'm wondering whether by allowing some, say, per unit royalty to be negative, like a subsidy will have any impact on the analysis. Maybe that's something, yeah, we can discuss maybe toward the end after.
I'm not sure it's legal even, because if you give per unit royalty negative, that means that you are the innovator, you pay me to produce. You can really change the competition to your benefit. But I think it's not legal, but I'm not sure about it.
Okay, because it will affect the efficiency of production, and you can always have fixed fee to extract whatever. Yeah. I don't know whether, yeah, so.
In the literature, it's not considered, but I think that maybe Debapriya and I once considered that, but I'm not sure.
Okay.
Okay, so this is the payment policies, and we consider the competition in Kuno fashion. So this is a Kuno N oligopoly, N firms. They are either with the technology or without the technology. And after the competition, the consumers will decide to buy, and it's homogeneous good. So this is the background. And here it's just to formalize what I just described. And there is a remark we want to emphasize. We only consider 3 instruments: fee, unit, and ad valorem royalties. We didn't include in our model a profit sharing mechanism. Because in the paper jointly with Stefano, we showed that for outside innovator, profit sharing is just equivalent to an upfront fee. So it's like a firm makes 100 net profit, and the innovator says, okay, pay me $20. It's equivalent to say, pay me 20%. So profit sharing for outside innovator is just the equivalent to a fixed fee. So we didn't include this mechanism, only the 3. And here, this is the parameter, the notation. Epsilon is the level of cost reduction. And K is the number of licensees determined by the innovator. N is the total number of firms. Okay. And our main results, we show that the maximum revenue the innovator can extract with any combination of the 3 instruments can be sufficiently extracted with just 2 instruments. And what are the 2? Is fee plus per unit royalty, and sometimes a pure upfront fee. Okay, this is the title, how we reduce from 3 to 2-part tariff. And we show this 2-part is F plus R. And what's more, we also show that sometimes a 2-part tariff with F plus ad valorem royalty can also achieve this optimum, but it requires some constraint. In the paper, we show this constraint to make this 2-part tariff with ad valorem royalty also sustain the optimum. That's the 2 general results. And these two results apply to general demand. Using these results, we solve for the linear demand case. And what's more, we show that if the demand is linear, then the diffusion of the innovation is almost maximized. That means all firms, and sometimes except one, will become licensees. Okay, so next, let me show you how we get these results.
Siyu, when you say general demand, you must have some conditions which guarantee unique Nash equilibria, because with a general demand, you can get non-unique Nash.
Yes, you're right. We impose 3 assumptions to make it.
Okay.
General means non-linear necessarily.
Okay. Literature review, I will just briefly talk about it. So we focus on cost reduce or process innovation. And in the old literature, most of the studies focus on 2-part tariff or fee. And here fee can be determined by auction or pre-announced. And they compare 2-part tariff or compare 2-part tariff with fee, but no one has ever studied all 3 instruments. There was one studying 3, but that applies for a new product innovation, and the downstream industry is a monopoly. So here we consider the strategic interactions in the downstream industry, which is Kuno oligopoly, and also consider the 3. So this is mainly our contribution to this field. Okay. So the model, we consider Kuno oligopoly, and the firms is from 1 to n. The set is denoted by capital N. And the inverse demand function is P of Q. And Q is the sum of all productions. Initially, the constant marginal cost is C. And if some firm adopted the technology invented by I, then the cost are reduced from C to C minus epsilon. And here are the first 2 assumptions we impose. Total revenue function is strictly concave in Q, P is decreasing and differentiable for P, and the price elasticity is non-decreasing function of P. So these are the standard assumptions for cost reducing literature. Later on, we have A3. Now let's describe the licensing game. Initially, there are n potential producers. And first, the innovator will put a contract A on the auction. And the A specifies the number of licensees he's willing to sell, royalty rate, and then anyone who's interested can put on bid. And let me explain why we determine it in the auction rather than pre-announce the fee by the innovator. There are 2 reasons we make this setup. First is the auction. In an auction, the innovator can actually extract more revenue from each of the licensee. And now let me show why. Because the willingness to pay for a license is determined by, let's denote it fee over bar to be the profit of a licensee with K licensees in this downstream market. This is how much he makes if he's a licensee. And now this licensee wants to deviate to be a non-licensee. So if he deviates to be a non-licensee, let's denote the profit to be fee lower bar. But now how many licensees are there in the market? Because it is on an auction. If he doesn't want, then the bid below him will become a licensee. So the next bidder will replace his place. will replace him to be a licensee. So his deviation doesn't change the number of licensees in the market. So the difference of these two terms is the willingness to pay for a license. Now let's see what happens if it's pre-announced. Pre-announced fee. In a pre-announced fee, the innovator will announce what? He will specify the fee and together with the royalty rate, such that in equilibrium, there will be K firms say yes to this contract, yes? And now let's see, what is the willingness to pay for a license? It is, if you're a license, you compete with another licensees in the market. Let me move it here. And now, if you deviate to be a non-licensee, you actually change the number of licensees, right? Because there are only K firms want this contract. If you don't want it, no one else will replace you. So now let's compare these two terms. For a non-licensee, he actually prefers to compete with one fewer strong players, right? So here he makes more. Then the difference in profits is lower. It means the willingness to pay for a license is actually lower if the fee is pre-announced. So for the innovator to extract more, we assume he put it on the auction. That's the first reason. And secondly, because it's K and K here, it actually simplifies our computation. So for technical reasons, we choose to put it on auction. Okay.
Let me just interfere to make sure that everyone understands. The contract, what is the contract? The contract is that I, the innovator, commit to sell at most K licenses, and a licensee will pay me R per unit and a percentage V of my revenue. And now you want this contract, bid for it. And the highest bidders will, K highest bidders will will get license and sign this contract. Thank you.
Okay, thank you. Okay, that is the first contract. What if the innovator intends to sell N, that is to sell to everyone? Then he has to specify the price for this contract. If he doesn't, he simply says, okay, I want to sell a license to everyone at this rate and this rate. Then everyone will simply bid zero because they are guaranteed to get one. So in this case, if he wants to sell to N, he must put a reserve price. So that's the difference if K is less than N or K is equal to N. Okay, so that clarifies that.
So now, ex ante, all the firms are symmetric. So of course, there exists symmetric mixed strategy Nash equilibria, symmetric Nash equilibria and mixed strategies. But you are focusing on pure strategy equilibrium.
Yes.
I'm wondering whether with mixed strategy, the average payoff is higher or lower, etc. But anyway, that's a side question. We can ignore it right now.
Oh, thank you. Okay. So now let's describe the game. Stage 1, the innovator chooses either contract K.
Since the profit is concave, I don't think it matters. I think the profits are concave. I mean, that's the assumption that the revenue is concave minus C times linear cost. Then I don't think that you get something different with the mixed strategies.
You're sure? Okay, maybe.
I'm not sure.
I don't know. Just asking.
Okay. No, it's strictly concave. So what can
you know? Even without innovation, in a pure Cournot model, mixed strategy can give some, and concavity. Mixed strategy can give something different. With just
if this is the case, maybe I'm not.
Yeah, I have.
Say is not correct.
At least in strategic market games, it is true that mixed strategy gives you something new with concavity. But anyway.
Okay, thank you.
Okay, Okay, we finished stage 1. Okay, clarify these two. And then stage 2, the firms will decide whether to bid for a contract or not. And if it's in, a firm will decide either to accept it or not. Then at the end of stage 2, the set of licensees L is publicly announced. Everyone knows who is licensee. And stage 3, all active firms, licensees or non-licensees, compete in quantities. Okay, so this is the game. We start our analysis from the last stage. Licensees and non-licensees will compete in quantities. With a marginal cost C minus epsilon and licensees with marginal cost C, the payoffs can be written like this. Okay. And the payoff of I here. This is the part from per unit royalty, the part from ad valorem royalty, and fee. And here we denote delta as a function for RV, like this. And with this notation, we can rewrite the profit function of a licensee to be this here. In the bracket, we see is P minus C minus delta. So this is the effective marginal cost. And we call delta to be the effective magnitude of innovation. That is to say, effectively, this technology reduces the cost by delta. Okay, so this is an important term, delta. And to solve this Kuno stage, we design a new game. We call it C hat. And what is C hat? We assume there are two types of firms. A strong type with C minus epsilon to be the marginal cost, and the weak type, weak players who have C as the marginal cost. And they compete in a Kuno fashion. And how many strong players? I'm sorry, this is not epsilon, delta, C minus delta. And they are K. K firms with this marginal cost, and N minus K with cost equals C. And they compete in a Kuno fashion.
Siyu, I'm not sure that Siyu, I'm not sure that you mentioned. I mean, how many some firms may not bid. Not necessarily when you want to sell to K will say yes. You are coming to that, or
no? That's later on.
Later.
Let's here. Okay.
Sorry, can I ask a question? I'm a bit confused about the auction itself. I thought that when the innovator offered a contract, he specified K, R, delta, and then the firms will bid. So when they bid, they pay an additional price for gaining the contract, or no?
Yes, and the price is fee. Is the fee they pay.
Oh, that's the fee. So
the bid is.
Yeah, the bid is not a fixed fee specified in the contract, or
no.
Is it?
It's not. It's determined in the auction.
But then when you write down innovator's profit, I don't see that. Maybe I missed something, so I'm a bit confused.
Here,
the
innovator's profit.
Right.
This is determined in the auction. This is the bid.
Okay, so then the fee in the contract is something else?
No. It's endogenously, the FI is endogenously determined by the auction.
Oh, okay, got it. Yeah, thank you. Yeah, I understand now.
Okay, everything's clear. So let's back to the Kuno competition. To solve for the last stage, we assume there are K strong players with a lower marginal cost and minus K with the original cost C. And after solving this, we have a standard Kuno result, right? And here, the delta is not the delta we see here. It's not the delta we defined in equation 3. It's treated as an independent variable. And later on, the innovator will put the R and V such that delta RV is equal to the delta star we solved for. Okay, so right now in the Kuno computation, we treat delta as an independent variable. Okay, I hope that clarifies. And how is our game in the third stage related to the C hat here we designed? We know that by default, the licensee's profit is simply 1 minus V times the profit in C hat. Okay. So strategically, they choose the same. They will behave the same. The third stage of our game is strategically equivalent to game C hat. Okay, so we denote phi over bar k delta to be the profit of a licensee in C hat, and phi lower bar to be the profit of the firm with cost C. And we can solve the game regularly. Here we just emphasize in the third stage of Kuno computation, a licensee simply makes 1 times V and 1 minus V times the profit of a licensee in C hat, and the non-licensee's profit remain the same. And by solving the C hat, we have the following result. Okay. Suppose A1 and A2 hold, and in the Kuno computation with different 2 types of firms, we have the following result. A licensee makes higher profit than a non-licensee, and its profit is decreasing in K, and the following. So this is lemma 1. Using the result, we can apply to the third stage of gamma. And here, we want to make another assumption, A3. This, the ratio here is strictly decreasing in K. And roughly speaking, it says the willingness to pay for lessons is decreasing in K. It makes sense, right? If you see a lot of players are already licensees, you don't want to pay much for lessons. Okay. And this can guarantee if the innovator put K licenses on auction, at least K plus 1 will put on bid. Okay, so let me emphasize. A3 guarantees if it's a contract with K firm, with K licenses, then at least K plus 1 will place a bid.
That's lemma 2.
Oh, okay. Thank you, yes. Okay, with this assumption, we have lemma 2. And here, there is an important restriction. You cannot charge a very high ad valorem royalty. Otherwise, if it's too high, then no firm will want this contract at all. And we will use this result to derive our constraint. And if you are charging a feasible ad valorem rate, the highest bid is what they make if they are licensed, if they are licensee minus if they deviate. And if they deviate here, they don't change the number of licensees. Okay. Highest bid is the willingness to pay. And at least the K plus 1 firms will place a bid. K of them will be randomly selected. So it avoids the case that the innovator announced K, but less than K shows interest. Then in equilibrium, we don't know how many firms will be the licensee. It avoids this complication.
I have to make a general remark for this audience. You cannot talk about equilibrium if the game is not defined. and your game is not defined, okay? Because you insist of talking about the contract and how you choose the licensees, okay? Before that is part of the definition of the game. So the game is not defined, and therefore the equilibrium is not defined. So in order to well define the game, you have to say, here is the innovator announces that he would like to sell K licenses. Okay? Now, at most K licenses. It may be, and he put R and V, okay? The royalty per unit and the ad valorem rate and the number of licenses. I'm ready to sell at most K licenses with R and V. And then you ask yourself, what happens if only, let's say K7 and only 2 say yes? What happens if 8 says yes, more than 7? And stuff like this. And also what happened, is it possible to have that once they have their willingness to pay, that will be the bid, the optimal bid? Is it uniquely determined the number of, because for the same number, for the same fee, you may have different number of licensees that are willing to pay this fee. So all this you should, I mean, it should come before we understand what is the game, especially the.
Yes. So one point in the definition of the game is not clear to me. Maybe I missed it. So suppose 8 people. There are only 7 licenses, and 8 people have bid for it. You choose 7 randomly, so that I now have probability 7/8 to have a license, or so do I calculate my payoff probabilistically, or he chooses some 7 and sticks to it? How is it random? If it's random, then I, who succeed in getting a license, will get it with some probability and not get it with the remaining probability. Is that the model?
I think the 7 highest bid will be selected, and if they bid the same amount, they will be selected randomly, but only the 7.
So supposing 8 people bid the same amount and only 7 have to get the license, K is 7, then each bidder will get the license with some probability and not get it with the remaining probability. Is that the model? So when he calculates his payoff in the game, he'll take an expectation.
I don't know. We don't take.
So what do you mean by random? 8 people have bid the same, 7 have to be selected. If the 7 is random, then I, who is one of the 8, will get the license with some probability and not get it with the remaining probability. That's not the game then. What is the game?
No, it is the game.
I see. So I calculate my payoff as an expectation in that game.
Yeah.
Okay.
It's not an expectation because all of them give you the same amount.
No, I get it with some probability and I don't get the license with the remaining probability because there are 8 people who have all bid the same. Only 7 have to get it.
So you multiply it by a constant. It will not change anything.
Maybe I don't see that either, but anyway.
No, that's fine. There's no problem for this. You choose at random 7 out of 8 at random. Okay. And the other one, yeah, you're right.
I won't get the license with some probability. And in which case my payoff is different. And when I get it, it's different. So I have to take an expectation over those.
You're right. You're right.
Is that the model?
Yes.
Okay. Thank you.
But if that's the model, we should multiply all these terms times the probability to get it, right? We didn't take that into consideration.
So what is the model? It could be that he picks the 7 whose names begin with the highest alphabetical order. He does not randomize. That could be another model. I don't know what the model is.
No, what Pradeep is saying is the model. Yeah, they take all these things into account. They do take expectations.
Okay, thank you.
Okay. Okay. So I hope we finished lemma 2. Okay, let me emphasize this is an important constraint, and at least the K plus 1 firms are interested.
So let me just say, Pradeep, if the lemma says that if he would like to, I mean, given the assumptions, If he announced K, okay, that he would like to sell K licenses, but willing to, but for the per unit royalty R and ad valorem V, then at least K plus 1 firms, this is a theorem, yes? At least K plus 1 firms, not less than K, not more than K, not equal to K, but at least K plus 1 will bid, and they will bid according to the highest bid is, you see, part 1, and K of them out of this bid, the highest bidders, obtain the license.
Randomly chose. Okay.
So it's not a case that you announce K 7 and only 2 will get it.
I got it.
Okay.
Thank you. Thank you. So here we continue to solve the game. The willingness to pay if he announces K, and the willingness to pay if he announces N. Here we replace N to, because it's a different function. So we denote it by willingness to pay over bar. Okay. And here, using the constraint we mentioned above, we define what is an acceptable contract, acceptability by firms. So if it satisfies these two constraints, then a firm will place a bid or say yes to the contract. So V cannot be too high. And now let's move on to the innovator's problem. We rewrite the innovator's profit, the revenue. So this is how much he can extract from a single licensee. This is from R, from V, and here we plug in the fee, the willingness to pay. And after rearrange the terms, we find it is only a function of K and delta, which means the impact of R and V is completely through delta, not separately. So the innovator's problem is reduced to choosing, instead of KRV, to choose K and delta. Okay, so the innovator thinks to himself, what is the number of licensees? What is the effective cost reduction I want to impose for them? Then we have the optimum solution. And to achieve this delta star, the optimum level, he can choose R and V accordingly, such that this is equal to delta star. Okay. And we find to sustain the delta star, there are an infinite number of RVs. So there are multiple optimal policies in a sense. That's the idea. And we also do it for the case of K equals N. The innovator's revenue can also be written as a function of N at delta. So that's the way to solve this problem. So now the innovator chooses delta to maximize his revenue as a function of K and delta. But don't forget, we have an acceptability constraint. The V cannot be too high. Okay, given this problem, let's see the result. Here, capital R of...
Can we go back to equation 3?
I'm sorry. Deba, what is your question?
The last equation. Yes, so what you can observe here that the first term is the monopoly profit at cost C minus epsilon at that price. So essentially, so that this equation has an interpret, it's useful to see that essentially the first term is the monopoly profit and the last term are the reservation payoff. So essentially the innovator is designing the contract so as to extract the monopoly profit at that price, leaving the licenses with the reservation payoffs, which is the payoff of a non-license.
Yes.
Yep.
Thank you for the explanation. Okay. So here, capital R of K defines the feasible range of the royalty. the per unit royalty. So any R in this range, it's okay. Okay, you cannot choose a too high R that exceeds the level of cost reduction, effective level of cost reduction. And the result is there are multiple RV combinations to achieve the optimal delta, and especially all two-part tariff FR can achieve this delta with no constraint. But if you're thinking about two-part tariff with F and V, you have to consider the constraint on V. And after rearranged terms, the V should be such that this hold. Okay. So in another word, we say the innovator can achieve the three-part tariff FRV. The optimum, the maximum level of revenue can be sufficiently achieved by FR. And if this condition is satisfied, a two-part tariff FV can also achieve the same optimum. Okay, and this constraint is by the acceptability constraint by firms. And here it's just a rephrase of, so let me skip this part. And proposition 2 tells basically a very similar story, but it applies to the case when K is equal to N. Okay. When K is equal to N, we have similar result. FV is optimal, FR is optimal, FV is optimal only if this happens. So it's a repetition, and let's see. The last part of our paper deals with a linear demand. So here we assume the inverse demand function is P equals A minus Q. And we solve the Kuno computation first, starting from the last stage, and we plug in the standard Kuno computation into the innovator's problem with the acceptability constraint. We have the following result. If N is equal to 2, and depending on the level of cost reduction, we have 3 regions, and in each region, we calculate the optimum policy. So if epsilon is small, he chooses a pure upfront fee scheme. If it's large, then he sells only to 1 and uses a pure upfront fee. If epsilon is in the middle, then he sells to everyone, both of the 2 firms, and there are multiple optimum policies. And we also summarize the linear case for general N. If N is greater than 3, the unique maximizer for I with respect to delta is given by this. If he sells to N minus 1. And if he decides to sell to N, then this is the condition for optimal delta. And to sustain the optimal delta, we have multiple choices on R and V. Okay, so we summarize our result in the table. This is just to tell you for each number of N, what is the optimal contract like. So here is the result. And that's it.
Good, thank you, Siyu. Any questions?
I have a question related to Pradeep's question. So I'm wondering if you say that when there are more than K firm bidding for the auction, you randomize, then wouldn't one of the firm bidding the highest bid can win that for sure by slightly raising the bid?
Yeah, but he will be better off not to be non-licensee in this case.
He cannot exceed his willingness to pay less than maximum. Otherwise, he's better off being a non-licensee.
No, but if you say when I calculate expected payoff, taking into consideration I only have a chance of getting a license, my expected payoff is equal to my reservation payoff, then if I slightly increase the bid by epsilon, there should be a discontinuous jump in my payoff from gaining the license, no?
In equilibrium, a licensee and a non-licensee make the same amount.
Right. So
if you raise it by a little bit, then you're better off being non-licensed.
So then I think isn't this the allocation rule, like if more than K firms bid for the license, then from the smallest number called 1 to, I don't know, like 7 will gain the license for sure. Larger than firm identity, larger than, I don't know, the first 7, they're not going to get the license.
That's the result. I'm not sure that.
So I'm wondering whether this actually corresponds to that allocation rule instead of randomizing.
Yeah,
between...
we are talking before equilibrium, right? We are talking about defining.
Yeah.
Defining the gain. Yeah.
Right.
So what is the problem? If you get more than K, you select at random K.
So this is something.
And then, every firm, every licensee obtains, has to pay the bid, plus later on paying the R and the V. Okay? In equilibrium, they will choose, their willingness to pay. But for that, you need that at least K plus 1 will be that willingness to pay. The willingness to pay of K should be at least K plus 1 should bid it. Okay? Now, what Pradeep says, expectation, it is true, but immediately after, there is the announcement of who is the licensees, who are the non-licensees. So you know that if you are a licensee or non-licensee, then you don't need to take, from then on, you don't need to take any expectation.
Right. But when I bid, I do need to.
Before this announcement, I'm still calculating the expectation because I calculate at all points in the game tree.
Yeah, but you're right. But in equilibrium, you're right on that. In equilibrium, you don't care because the licensee and non-licensee make the same amount. So you take an average of 2 equal numbers.
That's fine. No problem.
Okay, let me just mention, because we have another minute, just where, the main, why we need that assumption that's a little bit awkward, which is, by the way, is satisfied, A3, which is satisfied by a linear demand, but more than linear demand, but it is a constraint. Let me explain. First, you prove what we said by now, okay, that if you put K less than N, K less than N, the result is that you get at least K plus 1 bidding and you select at random K. No problem. Now suppose I want to put N. In this case, I know that if somebody deviates, the willingness to pay is a little bit different, because if one deviates, there are only N minus 1. You can show, actually, it is possible that given the willingness to pay of N, okay, if you charge it, you have to set it up, because there's no auction. Nobody will bid anything in this auction if you guarantee to give to everyone a license. So they would put 0. So rather you put the willingness to pay as a fixed fee, upfront fee. You want to pay me plus the R&V, you'll get the license. Okay. The problem is that if that N is the best and you set up the willingness to pay as a price, as a upfront fee, you may get that in the subgame, you may get it also K smaller than N will say yes and the other one will not bid. It's possible. In which case you are going to lose money. You make less because you get the same amount, but times K instead of times N. K is smaller than N. Okay? So what will happen then? You'll have multiplicity. What do you do? Okay. So the answer is that that cannot be in equilibrium, okay? In equilibrium of the game itself, not of the subgame. Why? Because then you can show that he's better off reducing from n to n minus 1. Once he reduces from n to n minus 1, you go back to lemma 2, where it's unique. At least then n will, I mean, at least n will buy, and you'll get, n will bid, and you'll get n minus 1 selected at random, and you get uniqueness. So this phenomena is actually is not an equilibrium phenomena of the game itself. It is a equilibrium phenomena of the subgame, but not of the game itself, because the innovator may then deviate to n minus 1. Offering n minus 1, you can show by the assumption A3 that in that case he's going to be better off.